Okay, so we're going to talk about oscillations, and so a couple important keys here. So this word period, symbol T right there. We have angular speed, okay, which we also sometimes use as angular frequency in the case of like right here. We have spring constant, which is relevant length, like for the pendulum, frequency. Okay, so this relationship right here is pretty important, both between the relationship between period and angular frequency and between period and frequency. And then, in addition, some other important stuff, okay, energy stored in a spring, Hooke's law, okay. And then here's the period formulas for springs and for pendulums. And there's some other stuff that's not on here that's really important to remember. Okay, the first is the conditions for simple harmonic motion. So when we have oscillations, the conditions, and some of them is A is equal to negative omega squared x. Another version of that is F equals negative kx. And the last one is that U is equal to, well, let's say that U is proportional to x squared. Okay, so any version of this means simple harmonic motion. And I really want to highlight this piece right here. Okay, if you see this format, sometimes you're going to need to determine what omega is and use that to write like a period formula in the form of one of these using this right here. Okay, the other thing I want to remind you about is this equation right here, where x is equal to x sub m, or the amplitude of the oscillations, times cosine of omega t, angular frequency. Remember, you can find this using this piece right here, and then plus phi. And phi has to do with taking the graph and shifting the axes to the left or the right. We don't care so much about that. I guess it could come up, but generally it won't. These are the important pieces, okay? And remember that you can get V and A using derivatives, so V would be negative xm omega sine omega t plus phi, okay? And A would be negative x sub m omega squared times cosine omega t plus phi. Okay, and then the maximum values for acceleration, for velocity, and the amplitude of the greatest position, the furthest away it will get. If you have questions about any of this stuff so far, remember you can go back and watch the videos. Also, one thing that's not on here that might end up being important, I just remembered, is the formula for a physical pendulum. T equals 2 pi square root of I divided by mgh, where I is the moment of inertia of the object, and h is basically the distance the pivot point is from the center of mass. Okay, on that note, there's a couple assumptions you make when you use this pendulum formula here, and that is that theta, or the angle for the amplitude of the pendulum, is small, like very small, well, relatively small, and also that L is constant. Okay, so like think of like if you had a string that was stretchy, and it's going to stretch at the bottom where the pendulum's moving the fastest, and it'll be shorter up at the top. So that would affect the period of the pendulum too. And so you're assuming that the length is constant. Okay, so let's look at a problem, an AP question. This one's actually from your packet, and there's a couple reasons why I like this one. But to get started, we are designing an experiment to measure acceleration from gravity, or g, at some unknown location. We have a pendulum swinging past a photo gate, and it's going to record time 10 for 10 oscillations, and it's a sphere of mass m at the end of the string length L, and we're going to try this with 4 different lengths. Okay, so we want to find t and the square of the period, and I'll talk about why we find the square of the period in a second, but really the first part, and this is legitimately from an AP test, you got to find t and square it, fill out the rest of this table basically. You probably get 2 or 3 points for filling out this table. So I'm going to quickly pause the recording and fill it out before continuing. Well, I'll do the first one. So the way that we get the period is by taking the time for 10 oscillations and divide it by 10. So this would be, t here would be 0.762. Okay. Okay, so we filled out the table, and actually I checked. You can actually get 4 points for this question, which, I mean, for filling out this table correctly. I mean, it's for really free points. You got to be looking for this stuff, and then it asks you to plot it: the square of the period versus the length of the pendulum. Okay, so as we do this, I just want to explain why you would do this. So the formula for the period of a pendulum is 2 pi square root of L over G. And when you graph this, it's a square root function looking something like this. Okay, but if you're analyzing data, sometimes it's easier to look at the data when it's linear. Well, you can take this data and make it linear if you square this equation. Okay, if you square everything, you get that t squared equals 4 pi squared times L over G, and what we write is t squared equals 4 pi squared over G times L. Now the reason this is useful is because now, instead of having the square root function, suddenly this represents a line that has a slope equal to 4 pi squared over G. And so if we were able to graph these data points and create a linear best fit line, if we found the slope of that line, it would be equal to this. Okay, so we're going to go ahead and do that. So at, let's see, 12 centimeters, that would be equal to 0.58. Here, I'll pause it for this part too. You don't need to watch me graph it. I plotted the points. I've gone ahead and drawn the line in yellow too, so you can see a little better. And again, drawing that graph, I mean, some more free points there. Okay, then it says, assuming that each pendulum undergoes small amplitude oscillations, from your fit, determine the experimental value of g of the acceleration due to gravity at this unknown location. Justify your answer. So that's where this part would come in. You would basically derive this, and then we'd say, okay, the slope of this line maybe is, you just kind of pick points on the line. So let's say that's a change of about from here to about, let's go with right here about. Okay, so that's like 11.2 comma 0.5, and this point is at 26 comma, and this would be about 1.2. So we want to find the slope. So that's an increase of 0.7. This is an increase of, let's say, 14.8. Okay, we can even convert this to meters, so that would be 0.148 meters. That's seconds squared. And so our slope here would be 0.7 seconds squared per 0.148 meters. We'll set that equal to 4 pi squared over G, and we'll solve this real quick. And so I get that 1 over G is equal to 0.1198, and I take the inverse of that to find G, and I get that G equals 8.35 meters per second squared, which is a little small. Okay, and it says if the measurement apparatus allows determination of G that is accurate to within 4%, are we in agreement? So 4% error, so the finding percent error would say 9.8 minus 8.35, and then divide by the original amount, 9.8. Then we multiply by 100 to make it percent. Okay, and so the math there is going to give us probably definitely more than 4%, probably closer to 7%? Or 14%, 15% actually. Okay, so we get 14.7% error. And so the answer here is no, because we have an error here significantly greater. Okay, it's quite a ways off. Okay, so, and then finally it says, someone informs you that the experimental apparatus is in fact near its surface, but that the experiment has been conducted inside an elevator with a constant acceleration. Okay, and so this is kind of bringing in Newton's laws. Assuming that your experimental value is exact, okay, so we got 9.8, or rather, sorry, that this is 100% correct, but it's been thrown off by the fact that the elevator itself is accelerating. It asks us to find the magnitude and direction of the elevator's acceleration. So the way we're going to do this is by thinking of like if the elevator was in equilibrium. So if it's moving at a constant speed, for someone standing in there, you'd have upward normal force and downward gravitational force, okay? And so this is the normal gravitational force. And so you'd say, well, MA is equal to Fn minus mg. And if it was at rest or at equilibrium, if moving at a constant speed, then 0 would be equal to Fn minus mg. So what's experienced when the elevator isn't moving is going to be equal to just mg. And so this normal force, what we experience as the force inside the elevator of gravity, we'll call it G for G experienced, is going to be mg experienced. That would be like, we can replace it right here. So MA equals G experienced minus mg. And we're going to say, so we said based on this that up is positive, okay? And so m is going to drop out of the equation, and so A is going to be equal to G experienced minus G, so that A is equal to 8.35, or the G experienced by the pendulum, minus 9.8, and that's going to be come out to be like negative 1.45 meters per second squared. Okay, so it's 1.45 meters per second squared is the magnitude, and the direction, since we said up is positive, it's negative, is going to be down.